Oh, well, it's hard to see. Yeah, well, I'll try to give up on that, but Becky, it's hard.
That's okay.
Okay, so today it's my pleasure to introduce uh, Becky Jensen-Clem. She got her bachelor's from MIT, uh, PhD from Caltech, Miller Fellow at Berkeley, faculty at Santa Cruz. I would say this is a fairly perfect trajectory. I met Becky, I think, in summer of 2011. She was a surf student at JPL, and she turned up in my office and said wanted to talk to me. I was became quite impressed with her knowledge of engineering, which turned out to be later after we admitted her. Not a surprise, Becky had in fact won the Lockheed Martin Prize for Excellence in Systems Engineering. It's a fairly prestigious prize at MIT for undergraduates. Becky wanted to work with me, uh, but I told her that I'm not interested in exoplanets. It's very fashionable, and in fact, was very interested in recruiting her to PTF. But she thought exoplanets is where the action is, which is correct. And so she began a project on an externally dispersed precision radial velocity spectrometer. Of course, I always have a soft corner for students who are interested in technical subjects. I always think the astronomy is the easy bit in our subject. And so I kept in touch with her. Unfortunately, a couple years into this, both her advisor and the postdoc was working, Phil Murray, both the advisor and the postdoc left. And Becky was without an advisor. And even though I was a director of a very CO with a lot of duties, I really was offered to be her advisor. So her proposed thesis topic was had two parts. One is high fidelity modeling of coronagraphic performance with attention to speckles, and the use of photon energy resolving detectors to combine that and to really go, to do both chromatic part of speckles and dark hole. It was quite an ambitious project, but Becky was an excellent student. So, the more excellent a student is, the more ambitious projects should be assigned. She made excellent progress on the first part, but found the basic theory for quantifying contrast was optimistic. In fact, her work is now a formal report of NASA's ExoPac Study Analysis Group. Separately, the second part of the thesis, the energy resolving detectors from UC Santa Barbara, Ben Mazin, they didn't arrive in good time. So things were desperate again. And I filled in by suggesting she, in fact, be fully in charge of roboticizing the 84-inch telescope and being the uncommissioned Robo AO. So working, can I have the screen, Mansi? The sharing?
Yes, it
okay.
should work now.
Sorry, it didn't come up. So here she is as the working with Reed Riddle, Dima Duev, Chris Barnack, who's a faculty at Hilo. Here's Selma, student of Chris, and this is the 84-inch telescope. And she managed to, in fact, pull it off. And finished her thesis and went off to Berkeley. I was a little disappointed that she didn't rake in a lot of fellowships in the sense of Berkeley. She had both the she had applied for 51 Pegasi fellowship and Miller. She got the Miller. Now it turned out the foundation, Heisenstein, was even more clever. They figured she'd get the Miller anyway. So she joined Berkeley, and in fact, they gave her a really, as a postdoc, they gave her a substantial grant for developing a adaptive optics laboratory setup. Becky is, I think, perhaps the most organized student that I've ever worked with. And I told her when she gave the Everhart lecture in her introduction, I said that I expect her, in fact, to either be PI of a very large instrument or become the administrator for NASA. That either way, her organization will take her very well. So it is a pleasure to see Becky again. And over to you, Becky.
Hey, thank you so much for that introduction, Shri. It's so nice to be here on the other side of the colloquium at Caltech. I learned so much and got so much out of these as a graduate student. I wish I could be there with you in person, going to the ath and chatting with you over wine and cheese, but we'll still make do with Zoom. I think that this is a particularly exciting time to be talking to you all about exoplanets because the TESS Space Telescope has started to bring in its haul of new exoplanets, and at the same time, we're all anxiously awaiting the launch of JWST, which we can use to characterize some of those planets' atmospheres. And at the same time, we have the Gaia data release that's about to come through in the next year that will give us many new planet parameters. And upgrades to the high contrast imaging systems at Keck, at Sphere, at Gemini are setting us up to directly image a much larger fraction of those planets. So this time that we're in now, on this verge of an era of detailed exoplanet exploration, I like to compare to the time period leading up to the launch of spacecraft like Voyager, the Pioneers, and Mariner, because those spacecraft introduced us to the planets in our solar system up close and personal for the very first time. And they showed the planets in our solar system to us as true worlds in their own right. And so here, just for fun, I wanted to show you some of those first early images taken from spacecraft of those solar system planets. So of course, Voyager, when it reached the outer solar system, it turned back and it took this famous family portrait with Earth suspended in a sunbeam. And it showed us that Earth was one planet among many and one point of light among many. But since the 1990s, with the discovery of now thousands of exoplanets, we began to put our solar system into the context of the full repertoire of planet formation in our galaxy. And this is a figure that you'll see in perhaps every exoplanet talk that you care to go to, because it has so much rich science embedded in it. It's plotting the planet's mass and Jupiter masses against its separation from its parent star in astronomical units. And the different colors represent different methods that we've used to identify these exoplanets. So of course you have transits, you have radial velocities, microlensing, pulsar timing, and direct imaging, which is the focus of my work. Now, in the next few years and in the next decade, this figure is going to look completely different. And that's because we will have many planets discovered via astrometric monitoring with the Gaia Space Telescope. And we're also going to have a large number of planets discovered via microlensing from the Roman Space Telescope, among many other discoveries, but those two will be key. So you can already tell from this figure that there's something unusual about the planets that we discovered through direct imaging, taking pictures of those planets. And that is that they tend to be high mass compared to planets in our solar system and the planets we've discovered. And also they're very widely separated from their stars. And that gets at the technical challenges of directly imaging exoplanets. And so that'll be the focus of the last part of this talk. So I know that on Zoom, it can be a bit difficult to remain attentive for a full hour. So the way I wanted to organize this talk is to just say a few quick words about why we directly image planets when we have so many other methods of exoplanet discovery. But then the rest of my talk will be in two parts. The first one is going to be about a way that we can take the best advantage of the photons arriving to us from directly imaged planets to squeeze out the most science per photon that we possibly can. And then I'll take a quick break. We'll answer some questions on that subject. And then I'll move on to the instrumentation work that I want to share with you. And that is how we might directly image new classes of exoplanets by improving our adaptive optic systems. And in particular, I'll be focusing on a technique called predictive wavefront control. And if those words don't mean anything to you, don't worry, I'll explain what each one of them means. Okay, so why do we directly image planets when there are so many different ways that we can use to discover the presence of exoplanets? There are many reasons. Among them, when we directly image a planet, as is done in this image from the Gemini Planet Imager, showing you the planet Beta Pig b, we can monitor the planet's orbit over time. And as we do so, we can combine that information with radio velocity information, and now more recently, astrometric monitoring, and we can measure the true masses of these planets, not just the minimum mass, which we can get through other means like radial velocities alone, but we can actually get the true mass of these planets. Now, not only that, but perhaps even more importantly, we can get a spectrum of these planets. Only two methods of exoplanet detection give you access to some spectral information. When we can see the planet transit and then a cult behind its parent star, we can obtain some spectral information that way. But when we directly image a planet, we're receiving photons from that planet. We can disperse that light into a spectrum. And by fitting models to that spectrum, we can understand some of the fundamental properties of that planet's atmosphere, such as its effective temperature, and also properties like the surface gravity. Okay, so far I've painted a pretty rosy picture of direct imaging. But you can already see from this figure here, there are many fewer planets that have been directly imaged than planets discovered through other means. And that points to the technical challenge, which we'll get to in the second part of this talk. But right now I want to point to a different kind of challenge, and that is interpreting information about the atmospheres of these planets. So what I'm showing here is an image of 51 Eri b, an exoplanet discovered by GPI. And there's some controversy about exactly how massive this planet is. But the most optimistic, meaning the smallest mass estimates, are around 2 Jupiter masses. And if true, that would make it the lowest mass exoplanet ever discovered. So in this panel, we're looking at a spectrum of 51 Eri b, shown by the dots with error bars, and then with a model in red fit to that spectrum. So first of all, you'll notice that the model fits pretty well at those shorter wavelengths in J, H, and K, but the model completely misses the data out in the longer mid-infrared wavelengths that you see here. So the folks who made this model said, you know, maybe the problem is that we haven't included clouds in our model of this planet's atmosphere. And of course, clouds play an important role in the atmospheres of our gas giant planets. So when you include some model that incorporates clouds, well, you're doing better at those longer wavelengths, but now the model completely misses the data at the shorter wavelengths. And furthermore, both of these models produce exoplanet radius estimates that are completely inconsistent with our knowledge of how these planets form and evolve. So if none of our models fit the data, that probably means that we're not including the right physics in our models. And so when I was a graduate student, I read a number of papers where the authors would say, well, we fit all these spectra, but they're systematic offsets, they don't fit properly, and it's probably because we don't include the right cloud physics. And so that got me thinking, well, how could we bring more information to this problem? How could we learn more about these clouds so that we can include the right information in our models of exoplanet spectra? And that's what brought me to this topic of observing exoplanets in polarized thermal emission. Okay, so polarized thermal emission is going to be a technique that we'll use to learn more about exoplanet clouds. So this is a sequence of images taken by the Juno spacecraft, and it's looking at Jupiter in Jupiter's thermal emission. And what you can see is that Jupiter's banded clouds would profoundly shape the SEDs that you would observe should you observe Jupiter as an exoplanet. And so, of course, when you're seeing those bright regions, that's when you're seeing in between cloud decks and you're looking deeper down into those hotter layers of Jupiter. However, the exoplanets that we've directly imaged today are much more massive than Jupiter. They're typically more widely separated from their host stars, and they're also a great deal younger and hotter. So would exoplanets have the same kind of cloud formations as Jupiter? So this is a color magnitude diagram showing the sequence of brown dwarfs as they go through the L-type brown dwarfs, more massive brown dwarfs, through the LT transition and down to the T-type, less massive brown dwarfs. Now, these brown dwarfs have similar pressures and temperatures in their photospheres as the directly imaged planets that we've currently discovered. So I've given two examples on this colored magnitude diagram of directly imaged exoplanets, HR8799c and 2M1207b, a planetary mass companion. So these objects have different types of clouds, of course, than Jupiter because they're so much hotter, they're more massive, et cetera. So they have clouds that are made out of silicates. An L-type object, be it a brown dwarf or a planet, is completely shrouded by these silicate clouds. Now, near the LT transition, these clouds disappear, and then the T-type objects are free of this particular type of clouds. Now, it seems that objects around the LT transition have some kind of patchy clouds. Perhaps they're banded like Jupiter, or perhaps they have some other patchy pattern. And why do we think that? Well, first of all, we see enhanced photometric variability at the LT transition. We see that in the J band, they get brighter, even though they have a fairly constant effective temperature as you march down the LT transition spectral sequence. And also, there are some amazing results here shown by Ian Crossfield back in 2014, where he used a technique called Doppler imaging to actually map the photosphere of a brown dwarf lumen 16, which also indicated some variation in cloud coverage. And it's a similar story for directly imaged planets. HR799c, for instance, requires a patchy cloud model to best fit its SED. And 2M1207b, just like LT transition objects, or many of them, it also has periodic photometric variability. So all of this is to say that brown dwarfs and directly imaged exoplanets, they have similar types of clouds and they behave in similar ways through the LT transition in terms of breaking up and then receding as we go to L-type objects. Okay, so before I explain how polarimetry can help us understand these clouds in more detail, I want to just give a brief primer on polarimetry in case it's been a while since anyone has considered polarimetric data products. So if we just imagine light's electric field, of course it has an amplitude and a phase. We can consider this electric field just at an arbitrary point in space, let's say r equals 0. Now we can break up this electric field into an x component and a y component. And of course, those two components will both have their complex amplitudes. And we can then take the real part of those complex amplitudes, and we can plot the result on the xy plane. And for most values of epsilon and phi, what you would trace out over time in the xy plane is an ellipse. That means we're tracing the tip of the electric field vector over time. And that for most general values, that tip would trace out an ellipse. That's what we call elliptical polarization. But for some special values of epsilon and phi, it would trace out a line. That would be linear polarization. Or for other special values, it might trace out a circle, and that would correspond to circular polarization. So observationally, we often quantify our polarization using something called the Stokes vectors. Stokes I is just the sum of the polarization states. That's the total intensity that we're all used to dealing with. Stokes Q and U represent linear polarization. So later, when I refer to Q and U, that refers to linear polarization. And V represents the circular polarization. So the clouds that shroud the atmospheres of these brown dwarfs and exoplanets are what induces the polarization of their thermal emission. So as photons from deep inside the planet or brown dwarf move through the atmosphere, they're scattered by these aerosols, and then the planet gets polarized at the limbs. So you see it's linearly polarized at the limbs. But of course, we don't resolve the disk of these exoplanets and brown dwarfs. We see them as a point source. And if you were to add up all the polarization in this disk, it would sum to 0. So in order for us to see some observable disk integrated polarization, we need to have some asymmetry in this picture. So these are models that just give a few examples of what the disk integrated polarizations would be for different asymmetric cloud models. So we have a banded model, a little bit like Jupiter on the left, and in the far right, we have a hodgepodge of patches, maybe like the Lumen 6T Doppler imaging results. And then of course, many of these objects are young, they're spinning quickly. And so having that extra amount of oblateness can also enhance the total disk integrated polarization. So here you see the disk integrated polarization is reaching values of 1%, 2% linear polarization, and more at times. So when I was a graduate student at Caltech, I did a fun side project, and I used the Gemini Planet Imager, GPI, to say, well, could we detect these small polarization signatures for point sources like exoplanets? And I found the answer was yes, we could absolutely get down to 1%. So that motivated me to keep going on this project. So what can we learn from studying exoplanets and polarized emission? Well, one of the key aspects is that polarimetry can differentiate clouds at different heights in a planet or brown dwarf's atmosphere in a way that the spectrum alone can't. So in this figure on top, you see the spectra of two different exoplanets, one with clouds at the top of the atmosphere and one with clouds a little ways down. And then in the lower panel, you see the polarized spectrum. And these models are quite different in polarized light, whereas they're very difficult to distinguish using the normal spectrum. So this is one of the examples where looking at a planet in polarized light can give you information about the clouds that you can't get any other way. Okay, so once I had shown that GPI could in fact reach these polarization levels that we would expect, I started doing a large survey at the very end of my grad career and then spent a lot of time as a postdoc working on this. So I observed 2 exoplanets and 5 brown dwarf companions to nearby stars using GPI and its European counterpart SPHERE. So what I did is I first looked at how oblate, so how crunched would these objects appear as a function of their rotational velocities, most of which were unconstrained at that time, although we're getting more and more rotational velocity constraints every day now. And as you can see from this figure, there are a couple different regimes, but of course the planets being very low mass, young objects would have been quite oblate, and the older lower mass, or older higher mass brown dwarfs, of course, would be less oblate, and we would expect to see less polarization from those objects. Okay, so we observed for many years with GPI and SPHERE. We refined our detection methods, and we were very excited when eventually we found that Rox's 42Bb was polarized. These were our Stokes Q and U, those linear polarization measurements for this system. So the fact that you see flux in Stokes Q and U means that we're seeing some polarization from this planet. But wait, you can also see that we observe flux from this background star that just happens to appear to be close to the host star. Well, it turns out that the star itself, this background star, and the planet all had just about the same polarization, and also the angle of polarization was almost exactly the same as well. And it turns out that Roxas 42 lives in the Ophiuchus cloud. And people have been observing stellar polarization from the Ophiuchus cloud for many years, because this polarization is not in fact intrinsic to these stars, but rather it's induced by the dust grains in the Ophiuchus cloud. So this was a plate from a publication in 1976, where these lines indicate how linearly polarized the light that they were observing from these different stars were. And I've indicated Roxas 42b here. And of course, its polarization was very much of a piece with other polarizations that we see from the Ophiuchus cloud. And the fact that the background object, the planet and the star all had a very similar polarization and angle supported the idea that what we were observing was in fact interstellar polarization. So undeterred, we went on to make use of our very sensitive upper limits that we placed on each of these 7 objects' linear polarization. So what you see here are representations of our upper limits. Those are the dotted lines you see here. So some of our upper limits, we were proud to say, were below 0.1% linear polarization. And then I'm also showing curves here. These are models of the planet and brown dwarfs polarizations as a function of their rotation angle or rotational velocities, assuming that we're looking at these equator on. And the polarization would be smaller as you rotated the objects to be pole on towards us. So this is the most optimistic case. So using those oblateness curves that I showed earlier, we calculated their polarization just as a function of their rotational velocity and hence oblateness. And our goal here was to place upper limits on how fast these objects could be rotating based on our polarimetry upper limits. And for most of them, even though we were achieving some of the most exquisite upper limits ever done in this capacity, they were not fine enough to actually intersect with these curves. So this shows, for instance, that these high mass old brown dwarfs, even if they were rotating close to their breakup speeds, it would not have been enough to exceed our upper limit. However, when we looked at our upper limit for beta Pictoris b, we found that our upper limit corresponded to a rotational velocity upper limit of 68 kilometers per second. Now, beta Pic's rotation has actually been measured already using high resolution spectroscopy. And so we know that its v sine I is 25 kilometers per second. So what we're hoping to do in the future is translate our additional upper limits that I'll describe to you in a moment based on our collaborators paper for objects that we don't already have a high resolution spectroscopy rotation period on to further constrain these objects' rotations. Okay, now another question that we started to ask ourselves was, well, we observed these 7 objects. We didn't observe polarized thermal emission from any of these objects. Did we get unlucky? Was this a fluke? Perhaps our models were over-optimistic in saying that these objects could be as much as 1% polarized. So what's going on here? Well, at this point, I was collaborating with a finishing grad student over at Leiden Observatory, Rob Van Holsten. And Rob and I expanded our survey to include almost every directly imaged exoplanet for which you could possibly get lower than 1% polarization. And this figure shows some of those objects in our survey. And we also found that with 1 or 2 exceptions, which I'll tell you about in a moment, we found no polarized planets. And the ones that we found to be polarized, it was due to circumplanetary disk material, but not due to scattering by clouds in their atmospheres. So deepening the mystery, here at Caltech, Dimitri Maway and project scientists Max Miller-Blanchere, who's now an assistant professor at UC Santa Barbara, were hunting for polarized brown dwarfs using the recently upgraded work-pole instrument at the prime focus of the Palomar 200-inch telescope. So work-pole is perhaps the best situated instrument to do this kind of precision polarimetry work on free-floating or field brown dwarf objects. And that's because being on an equatorial telescope, there's no differential motion of the optics. So the amount of instrumental polarization that you would get is stable over time. And also being at the prime focus, there are few reflections. So this was the best place to do these kinds of measurements. And yet, even though previous studies have found that many brown dwarfs are polarized at around 1%, between 0.1 and 1% in the near infrared, for many of these objects, when work-pole observed them again, they also didn't find any polarization. So we have something of a mystery on our hands. Could it be our models are overestimating the amount of polarization? Could it be there are systematic uncertainties that we're unaware of? Or perhaps it could be that the weather on these objects is much more variable than we realize. So perhaps these objects were highly polarized at the time that these authors made their observations, but they may be less polarized now. Now, adding further to this mystery, our collaborator, Max Miller-Blanchere, who I just mentioned, observed lumen 16A and B, this brown dwarf binary system, using NACO on the VLT right before NACO was decommissioned. And what Max found is that both components were polarized and likely polarized due to the presence of clouds, but only by very, very small amounts. So the A component was 0.03% polarized and the B component was 0.01% polarized. This is below most of the measurements that we were able to make with GPi or sphere. And what he found was that the B component's polarization could be explained just by an oblate atmosphere. And because the rotational period of this object was known, he knew how oblate it was, or approximately how oblate it was. However, the A component could not be explained by oblateness alone. So he went on to model banding in these planets' atmospheres and found some examples of banding patterns, such as the one circled in green here, that would explain this polarization measurement. But of course, these polarization values are much lower than what we could have detected with GPi or sphere. Okay, now I want to tell you the optimistic part of this story, and that is that our collaborator, Rob Van Holstein, focused his survey, in addition to searching for polarization due to clouds, also for searching for polarization due to circumplanetary or circumsubstellar object material. And in fact, he was successful. So in this paper that we recently had accepted, he observed the brown dwarf to planetary mass companion, depending on what your personal math threshold is, DH tau B. And this is a picture of DH tau B in polarized intensity. So Rob found that this object was 0.4% polarized in the H band. Now, fortunately, we already knew how fast this planet or brown dwarf was rotating. Caltech graduate student Jerry Juan, working with a Caltech graduate, Marta Bryan, found that the object was rotating with a v sin I of about 10 kilometers per second. So we didn't have to worry about Oakley-induced polarization in this case. And this object also had many indicators already of a circumsubstellar object disk, such as the hydrogen emission lines and the near-infrared colors. So the polarization is likely coming from the scattering of the companion's thermal emission by this dust that encircles it. And of course, we don't spatially resolve that circumsubstellar object disk. So Rob and his collaborator, Thomas Stolker, went on to model possible circumplanetary disks that could explain this polarization measurement. And this is an example of one of those models. So here the lines, again, indicate the degree of linear polarization. So even though you see the most polarization towards the outer edge of this disk, most of the flux comes from the inner edge of the disk. So the total polarization that we're observing mostly depends on the inner radius of the disk and the surface density of the disk. And so I don't want to steal all of Rob's thunder for his fascinating results, but he was able to place constraints on the inner radius and the surface density of the disk. And so I refer you to the paper to learn more about those. Now, interestingly, ALMA has not detected a disk around this object. And so future observations informed by Rob's constraints on the inner edge of the disk and the surface density are going to be a great area for follow-up. Now, Rob also found another brown dwarf companion with disk indicators that's also perhaps polarized, but it was a bit more difficult to distinguish whether that was due to intrinsic polarization or polarization due to interstellar dust. Okay. Now, I told you that one of our suspected problems is that polarization due to clouds in exoplanet and brown dwarf atmospheres may be more challenging to observe than our models indicated. So that means that having an instrument that can observe very precise polarimetry signals in a high contrast context is going to be particularly effective. And that's what Dimitri Max-Muller-von Scher and others, including myself, are interested in doing with Keck NERC2. So in this effort, we would do imaging polarimetry from the J to the L band with NERC2, and we would be able to combine those capabilities with coronagraphs and adaptive optics. So this project has already gotten underway, and we look forward to eventually using NERC2 in a high contrast polarimetry mode as well. Okay, that is the end of part 1 in this talk. I'm happy to pause to answer any questions before moving on to the instrumentation component.
Thanks, Becky. So raise your hand if you have a question for Becky, and then you can unmute yourself and turn on your camera if you wish to do so. So I have one question from Ranga. So you can unmute yourself and turn on your camera.
Hey, Becky. So looking at the polarization vectors in the star, which has got a disk around it, presumably this is all scattered emission, right? And so the grain is aligned with the polarization vector, which means that the magnetic field is threading in the plane of the disk. Is that what's happening here?
Yes, the magnetic field is threading into the plane of the disk. Yeah.
Is that expected?
So this is an area where I don't claim much expertise, but I believe this is something that Thomas Stolker, who led the modeling aspect of this paper, did address in this paper. So I would refer you to that for more details.
Okay, thanks.
All right, we have a question from Lynn.
Hi, Becky. Yeah, I'm curious, since this may come into the rest of your talk, what is your threshold for calling something a planet versus a brown dwarf?
Yes, so for a long time, the party line had been 13 Jupiter masses due to the deuterium burning limit. But a lot of folks, including Marta Bryan, have recently argued that it has more to do with how the planet formed, not having to do with whether or not it ever burned deuterium. So I would place my threshold based on whether that object formed in a disk as a planet would, or whether that object formed as if it were a binary companion to that star.
Okay, so we have another question from Pradeep.
And what is that?
Oh, 3. Yeah.
And what's the number?
Yeah, well, I mean, so then that would vary depending on the circumstances. So depending on the mass of the star, for instance, and the extent of the disk, but it would be somewhat higher than 15 Jupiter masses. So probably 15 to 20 would be a better threshold.
Okay, thanks.
Pradeep?
Hi, Becky. Forgive my ignorance of directly image exoplanets, but are there any candidates where there could be like a companion planet which could induce more, like, which could induce a greater degree of lateness due to like tidal forces?
Oh, you mean could you have, say, a binary planet system that would induce tidal forces? Yeah, I mean, there are tight binary brown dwarf systems that are themselves orbiting a main sequence type star. So that could happen. I don't think we have any directly imaged planets like that, but we do have brown dwarfs like that. So that's an interesting point.
So we have another question from Wenbin.
Oh, hi. So probably it's a very naive question. So there is some small fraction of the stellar light that's being reflected by the planet, even in the infrared band, right? Is that not enough to explain the to induce some small amount of polarization? Because only in the day side of the planet is reflecting.
Yeah, so fortunately or unfortunately for us, depending on your perspective, these objects, they're quite far from their stars. And so the amount of light that you would have reflected by the stars is going to be extremely low compared to their thermal emission and these near infrared wavelengths that we're observing them. So that wouldn't explain these kinds of signals for us.
Okay, thanks.
Have you considered gravitational darkening so far? Because that could be, given the rotational, so angular velocities you're looking at, that could be another factor that could play a role in the polarization.
Yeah, it's a good point. So the models that we used when I indicated them here, these did not include gravitational darkening. So that's a good point. It's something to include in the future.
All right, I don't see any other hands, so if you want to continue.
Okay.
Thanks.
Yes, thank you for your engagement. Okay, so at this point, I want to address why there's such a small number of directly imaged exoplanets on this diagram compared to those discovered via other techniques. And there are, of course, many reasons for that. But something that we learned on the basis of the many direct imaging observing campaigns that have now taken place is that the occurrence rate of these high mass planets at wide separations that high contrast imaging surveys are sensitive to is just very low. So Brendan Bowler in 2016 did a meta-analysis of several dozen high contrast imaging surveys and found that the occurrence rate of planets in this parameter space is less than 1%. So there just aren't very many planets in areas where modern direct imaging instruments can detect planets. But what this diagram shows is that if we could push our capabilities inwards to planets at smaller separations, then radial velocity and other studies indicate that there will be many planets there for us to find. So how can we do that? Well, of course, what sets how close to a star that we can detect a planet has to do with the diffraction limit. So in the famous airy disk, we're not going to be able to see a planet that's closer to the star than 1 lambda over d. So it'll help us out to have, of course, larger telescopes. That'll help us push inwards as well. And right now, the largest telescopes are going to be on the ground. So we have our 6.5 meter James Webb Space Telescope about to launch. But of course, our largest telescopes on the ground are already 10 meters, and we're looking forward to the 30-meter class telescopes. So we're going to have to deal with ground-based data for the next foreseeable future when it comes to high contrast imaging. Of course, we're looking forward to the CGI, the coronagraphic instrument demonstration on the Roman Space Telescope, but we still have some time to wait before a dedicated space mission for these kinds of projects. So when you observe on the ground, this beautiful, perfect, airy PSF is going to be aberrated by the Earth's atmosphere. And how does this happen? So I wanted to include this explanation just to bring everybody on board with what adaptive optics is, since that's what I'm going to be discussing. So if you imagine the electric field of the starlight being emitted by a distant star, you can consider a surface of constant phase in that electric field. So you can imagine that as being the crest of one of the circular waves emanating out from that star. And that surface of constant phase, we're going to refer to as the wavefront. So by the time those wavefronts have arrived on Earth, of course, they're stretched out, they appear flat. And those wavefronts are going to encounter the Earth's atmosphere. And the Earth's atmosphere has different pockets of air with different temperatures and other different properties. Now, when they pass through these different pockets of air, they're going to be delayed by different amounts. And that aberrates or changes the shape of the surface of these wavefronts. And so the result is when we observe a star with a telescope like Keck, we don't see this perfect airy ring as you would if the telescope was in space, but instead you see this incredible mess. And furthermore, the incredible mess moves with time. This is what you would see in many short exposures. And if you were to take a very long exposure, you would see the average of this giant mess, and that would give you a point spread function that is much more spread out than the airy disk. Instead of having to do with the size of your telescope, it has to do with the characteristic turbulent cell size of the atmosphere, which is called R0. Okay, so we want to find some way to bring the starlight back into that airy disk shape. Then we're going to suppress that airy disk using an optic called a coronagraph, and then we're going to be able to see planets next to that star. And the way we do this is using an adaptive optics system. So we take our aberrated wavefronts, we bounce them off of a deformable mirror, we break off some of that light, oftentimes the shorter wavelength of light, and we try to measure the shape of those aberrations so that we know what shape to give our deformable mirror to precisely cancel out those aberrations. And of course, there's many ways to do wavefront sensing, and we don't have time to go into that here. But the point is that we can change the shape of our deformable mirror. We can introduce these coronagraphic optics to suppress the star's airy disk, and that allows us to directly image these exoplanets. Okay, so adaptive optics systems for ground-based telescopes aren't perfect. There are many different terms in an AO error budget. One is you only have so many deforming elements on your deformable mirror. And right now, we're in the process of proposing for an upgrade for the Keck telescope that would give us a higher actuator count on our deformable mirror. Also, you only have so much light that's hitting your wavefront sensor, so you only have so much signal to noise in your measurement of the shape of the wavefront, so you might be giving your deformable mirror slightly the wrong shape as a result. Also, there are always going to be some optics that occur after your AO system. And if there are imperfections in those optics, they're going to introduce aberrations back into that starlight that you're not going to be able to measure and therefore not correct with the deformable mirror. But where I've been focusing my efforts recently is on another error, and that is the time delay in the adaptive optics system. So it's going to take you some time to collect the starlight that you need to measure the shape of the wavefront distortions that you require to change the shape of the deformable mirror. And this isn't a problem that is ever going to go away in adaptive optics. And that's because you're always going to have to gather some starlight in order to get the signal you need to measure the shape of the wavefront. You're never going to have that exposure time down at 0, right? So this is a problem that we're stuck with for the long haul. And where do these time delays come from? Well, this is a figure showing where the AO system's time delays come from for the pyramid wavefront sensor detector at Keck Observatory. So the total delay or latency is about 1.5 milliseconds. Some of it comes from that exposure time on the wavefront sensing detector. Some of it comes from the readout time of that detector, from translating that information onto the computer, and then from the time it takes for the deformable mirror to actually take on the shape that you asked it to take on. So this time delay error is extremely important for the performance of coronagraphic high contrast imaging instruments. And that was brought home to us when there was the analysis of the performance of the Gemini Planet Imager and of its European counterpart Sphere in the last few years. So this shows GPI's contrast, so how faint of a planet can it see compared to its star, as a function of the AO bandwidth error, which is related to that time delay. And what they found is that the time delay error was a strong predictor of how well they were going to do in their contrast. And of course, when the atmosphere is changing more rapidly, that increases the impact of this time delay error. So that's what we're seeing here. Okay, so what I got interested in as a postdoc was how could we mitigate this time delay error? And just at that time, there was this amazing paper that came out by Olivier Guillon and Jared Males down at University of Arizona. And their paper was the latest in a long line of papers for a topic called predictive wavefront control. So we're trying to control the shape of that wavefront, and we're trying to predict what the shape of the wavefront will be one time lag from now. So that's what predictive wavefront control means. So how do you do it? Well, there have been many proposals over time, but I want to tell you what Olivier and Jared proposed. So they said, let's represent our wavefront as some series of measurements, and let's put our last wavefront into what they called the history vector. And let's not just put the last wavefront in the history vector, but the last 10 wavefronts. Okay, now we want to find some magical filter F that when we apply it to that history vector, we minimize in the least squared sense the difference between the result and what the wavefront will actually look like one time delay into the future. So this is setting up the problem in just a straightforward least squares way. If we take a long training set of data, which we can use to stand in for the history vector and the true future wavefront, then we can solve for F in the least squared sense using that set of training data. And so this is what I sought to implement in collaboration with Sylvain Cetre and Charlotte Bond, who are both then at WMKO. So we were fortunate to take advantage of this new pyramid wavefront sensor that was installed as a testbed instrument a couple years ago at Keck. And there were some great things about the pyramid wavefront sensor that allowed us to do this test. And chief among them was that it had its own real-time control computer. And it was full of modern equipment like NVIDIA GPUs, among other things. And it was set up in such a way that we could get in there, get our hands dirty, and work on this code. So our first test of predictive control we did, of course, during the day. We simulated turbulence, we played it on the deformable mirror, and then we tried to predict it. And this figure shows our first results. So the red shows what we would have seen without any AO control at all. The green shows what the non-predictive AO control would have given you. And then the blue shows what predictive control gave us. So this gave us some confidence that we had implemented predictive control successfully during the day. And next, of course, we tried it at night. And things don't always go quite as you want them to go at night compared to how they act in the lab. So what this figure shows is similar to the first figure, except it shows that at night, our predictive control in its first implementation does about as well as non-predictive control. And it has a few stability issues, but overall, it runs stably throughout the night. So this is where we were at the very beginning of this year. Now I'm fortunate to be working with a postdoc, Micah Van Kooten, and graduate student, Jules Fowler, to help improve the performance of predictive control. And on Halloween night, we did our first test of predictive control where we were able to take data with NERC2 with the vortex coronagraph in place, because our science goal is to not just improve the AO performance in general, but also to improve the contrast for exoplanet detection. And what we found is that the predictive controller eliminates some undesirable behavior. So you see these two wing-like patterns that were present in our coronagraphic data with the non-predictive control, and you don't see those with the predictive control. So that was a small victory. But unfortunately, you do see other features such as this ring around the star that are enhanced when we use predictive control compared to the integrator or non-predictive control. So we have a lot of work to do in terms of optimizing all the different parameters that go into this filter, but we're making steady progress. Our next night for observations is Christmas. I got cursed with all the holiday observations this year, but we're excited to show you the results of those in the next few months. So stay tuned for more. Okay, now I told you about a lot of different error terms in the AO budget, right? Not just the time delay error, but there were also errors due to, for example, these optical elements that come after the AO system. So for this, among many other reasons, many of us are interested in measuring the shape of the wavefront just from the focal plane. So this is a technique called focal plane wavefront sensing, and there are many ways of doing this. But the one that I want to highlight here is called the self-coherent camera. So this was proposed in the last decade, and it involves a special type of optic that occurs as part of your coronagraph. And in this optic, usually you would completely suppress starlight that would have formed a ring in this image. Now, what this particular type of device does is it lets through a strategic amount of starlight through a pinhole. So then when you look at your camera images, instead of seeing your speckles and your planet, you would see this set of interference fringes because you've interfered the starlight with itself. So every bit of remaining starlight now has these interference fringes superimposed. And you can use these interference fringes to back out the phase, which you could then correct with a deformable mirror. But the difficulty with a self-coherent camera was always that not very much light went through that pinhole. And so your ability to detect these fringes was always pretty limited. So that's when our new UCSC postdoc, Ben Girard, came into the picture. He designed a special coronagraph that threw a lot more of the light out onto that pinhole. And in fact, he boosted the intensity transmitted through that pinhole by 6 orders of magnitude. And that was a total game changer for the self-coherent camera technique. So what he found is that if you were to measure your contrast, for example, here at 10 lambda over d separation, and if you were to measure your contrast as you increased your exposure time, and if you could measure and mitigate those wavefront aberrations using the fringes in the self-coherent camera technique, that his approach would allow that contrast to reach almost the photon noise limit in terms of how it improves with further exposure time. And if you were to extrapolate these curves out to a 1-hour exposure, Ben's technique, which is called FAST, could potentially give you 100 times raw contrast gain. So this is extremely exciting. Ben is now in the process of implementing FAST on GPI as part of the recently funded GPI Cal 2.0 upgrade. He's also working on developing FAST in our laboratory setup, which we're developing at UC Santa Cruz, and also for Scales, an upcoming mid-infrared IFU for Keck as well. So Ben is taking this technique in a lot of different directions, and I encourage you to stay tuned for more results. So to place predictive control and focal plane wavefront sensing techniques like FAST in the context of future exoplanet missions, this is a figure from the recent, well, now a couple years old actually, a National Academy of Sciences Exoplanet Science Strategy report. And it shows you some performance curves in this plot of basically contrast versus separation of existing instruments. It gives you some different simulated populations of planets, and it tells you some of the sensitivity limits that we might expect to see from space-based missions. What you see here are the performance estimates for the next generation of giant segmented mirror telescopes. These are the 30-meter class telescopes like TMT, GMT, ELT. And you can see here that we're pretty uncertain about the performance of high contrast imaging systems on those telescopes. And that's because we're still working to optimize our performance on existing telescopes using these advanced techniques like predictive control, focal plane wavefront sensing, having the highest order deformable mirrors, etc. So this lower curve here is what the performance we would expect to achieve with all of those advanced techniques implemented at their greatest possible performance, whereas the curve up here shows the kind of performance we would get if we just put our existing instruments on these larger telescopes. So this enormous performance gap shows you how important developing these new AO techniques are for the future of high contrast imaging. But there's a final piece of this puzzle that's missing. And that is, how can we expect to predict the performance of these future instruments if we don't know how to simulate atmospheric turbulence very precisely? And so this is where UC Santa Cruz postdoc Dr. Micah Van Kooten, who I mentioned earlier in the context of predictive control, is making a contribution as well. So Micah has been looking at the long-term stability of the weather on Mauna Kea. And she's been doing that by looking at a combination of summit weather data, data from balloon-borne instruments called radiosonde. And these instruments measure aspects like the wind speed, the temperature, the relative humidity, et cetera. And she's also looking at these global weather forecast models that are calibrated based on data like radiosonde. And these, listed with their acronyms here, are the American versions and the European versions of these large-scale models. Unfortunately, these models, one of them centers right on Mauna Kea, and another has a fairly large grid size, but also includes the Big Island of Hawaii. So just to give you a taste of what she's been finding, she was able to look at the wind speed measurements from the meteorology weather station that gives us data at 10 meters up on the summit. And by looking at this wind speed data, she was able to calculate what fraction of the time the domes would have been closed due to high winds. And she looked at what fraction of observations would have been closed due to high winds over time. So this is from 1996 to 2020. So she's broken it down here in different seasonal bins, and then also in black, you see all months put together. And so she's still working on the statistical analysis of this data, but there's some suggestion that winds might have been overall increasing over time. And finally, Micah has also been looking at the strength of the turbulence as a function of height, and that's what these CN² profiles are referring to. And so she's been reconstructing these profiles using different data sets and comparing them with the mass data from CFHT on the summit. And so she's also been analyzing how these turbulence profiles may have changed over time. And this work is still at a preliminary state right now, but what it highlights is that we have to be prepared to simulate different turbulence strength profiles over time when we're considering modeling the atmospheric turbulence for the purposes of future high contrast imaging telescopes. Now, interestingly, these large-scale weather forecast programs that she's been using in this analysis also predict what the weather will be like far into the future, and that could be another great future application of this work as well. So stay tuned for Micah's paper on the long-term weather changes on Mauna Kea coming out in a special edition of the journal Atmosphere in the next few months. Okay, so I just want to wrap up by saying that I argued at the beginning of this talk that we're on the verge of a detailed era of an era of detailed exoplanet characterization. And the reason I think that's true is because adaptive optics is now widely used at large observatories all over the world. We've now had our first generation of purpose-built exoplanet imaging instruments, GPI and SPHERE. And now we have emerging capabilities, both in terms of targeting our exoplanet imaging surveys. We have slews of exoplanets that will be discovered by Gaia and later the Roman Space Telescope. We can use those planets, say discovered by Gaia, to give us directed high contrast imaging surveys, whereas before we've done blind surveys only. We also have many new techniques and technologies, both software and hardware, that are allowing us to improve the performance of our current direct imaging instruments as we prepare for the future 30-meter class telescopes. So with that, I'm happy to take any questions. Thank you.
All right, thanks, Becky. So again, raise your hand if you have any question. All right, so I'll start. So do you see any, I see a trend in the wind maybe, pending statistical analysis, but is there any other trend? It's hard to read from the CN² profiles, but do you guys see anything evolving since the 50s?
For the CN² profiles, right now, Micah is still in the midst of calibrating all this data and making sure we really understand what we're seeing. So the shaded regions here represent the standard deviation of these data sets. And so, I mean, just by eye, like there do appear to be changes, but to what extent those are significant or not, that's still something that Micah's looking at. So I would say we can't say anything just yet, but she hopes to soon.
Mm-hmm. All right. Questions?
this is Shri. I have a question and I can't raise my hand.
Okay, go ahead.
Yeah. Becky, back to that predictive algorithm.
Yeah.
I mean, this has been around for a long time, right? Let's say
Yeah.
I have a missile and I have a target, then I'm making all my sensor measurements, and then I'll use my history and I'll use Kalman filtering as I approach my target. So what's new?
So what's new about this is really that we now have the computing power to implement these techniques in real time.
Well, no, I understand that, but what's new in the algorithm? Because why is this not a simple Kalman filtering problem?
Yeah, so the Kalman filtering is just another extremely related way of solving this problem. There's really nothing fundamentally different between how these techniques would perform. So Lisa Poinier, she proposed a Kalman filtering method of predictive control that didn't end up getting commissioned on GPy just due to lack of time. So the answer to your question is really, there's nothing particularly new here. We have a very simple implementation that now we're able to implement inside Keck for the first time. So that's what we're aiming to do.
Oh, okay. And the question I had is, so obviously there's some irreducibles in this game, which is the integration time.
Yeah.
Okay.
Let me go back to this.
I mean, I can come up with some really crazy ideas by which I will take the planet light, which is a different band compared to my signal, and let's say I have a way by which I slow down the light and put it in storage while I figure these things out. So let's say these are all hypothetical, but there's another one which I know, which is the velocity of those the clouds, which I have no control of. So are there some special times of the year when those jet stream is reversed in Hawaii that you can make measurements because the winds are very slow?
I mean, this is really the question that Micah's work is aiming to answer, is that are there times of year when the atmospheric parameters are more favorable than others? So that's what she's on the road to discovering, but I don't think we have that answer now.
Oh, that's excellent. I mean, that's I think that's the way to go. Yeah, that's it.
Thanks.
Thanks, Sri. Any other questions?
This is Bin Ren.
Yes, go ahead.
Hey, Becky, can I take a look at the NERC2 image after you applied the predictive wavefront control?
Yes.
And is the secondary ring the secondary area ring, or it's some artifact?
No, this is an artifact from our control. It's not the second area ring that's much closer in.
Okay, thank you.
Yeah.
All right, any other questions? So if not, then I'll invite the faculty to stay on for the meet and greet, and thank everyone and thank the speaker again. So thank you, Becky.
Thank you.